Autonomous drone delivery has moved out of the realm of science fiction and is already taking place in deployments all around the world. And the aircraft that make these deliveries, like the ones used by Wing, have to be designed from the ground up. We visited Wing's workshop and labs where they dream up new aircraft, engineer them for the task of automated delivery, and have even built a wind tunnel to test custom propellers.
All right, Adam, what does this platform represent here?
So we affectionately called these the stick planes for obvious reasons.
Yeah.
But it was sort of like after we'd sort of generally coalesced on a design. So picked how big it should be, picked sort of how much it should carry around, the general configuration. We wanted to make them actually sort of like do all the automated pieces. So like, can you figure out the charging? Can you do all the precision hover bits? And like, you don't need the rest of the airplane to do that.
Right, this was a platform on which you worked all that out.
Yeah, just working on the propulsion system, some of the guidance stuff. And so we built a handful of these just to demonstrate like the architecture worked.
Right.
And
they worked.
They worked, yeah. So I think it was, the task we were given was like, in a inside shop, like, make the plane take off and land 1,000 times in a day, or do it without like people touching it, and sort of figure out the key automation pieces.
So in your early ideas about what you needed to get through to get to flight, this was like, this was working and everything was going.
This was sort of step 0 or -1 or whatever you want to pick. You got to start somewhere.
Yeah. And I see the motor controller is strapped to the sides and all of that stuff.
Yeah, so super boilerplate, but all the relevant sort of electronic pieces. So you have the sort of motors you're going to use, you have the motor controllers you're going to use, you have a stand-in for the avionics, all the pieces that sort of do all the automated flight parts.
Okay.
Once we got all that stuff working out, it's like, okay, you got to wrap an airplane around it.
Yeah.
And this was in probably 2016, 2017, sort of early days of the program. We thought we were going to build like a conventional airplane.
In terms of durability and...
Yeah, and just the materials you use, the processes you use. So we're going to build it like you'd build a small composite aircraft. So we built these, which,
Oh my God, that feels so amazing.
Yeah, it's like a conventional sort of built on hard tools.
This is vacuum bagged.
Yeah, all vacuum bagged in,
It's
and then
like half a millimeter.
It's very thin stuff. It's
Oh
just
my God.
like everything optimized around weight.
Was like,
It's probably a pound or so.
Yeah,
It's like very light structure.
Crazy.
Really precision airfoils, sort of trying to build what you would think an airplane should look like.
this is like what a kid thinks model airplanes are.
Maybe a little less balsa wood and monocoque, but
Yeah, no, it's so pretty. Okay, so you built these.
So we built a handful of these. So here's one with sort of all the electronics out of this in this.
Okay.
And we flew them.
Which must have been awesome.
It was cool. They looked really cool. They sounded neat. Like there's a cool like vibration you get inside. It makes a hum with the hollow structures.
This is a really expensive way to build.
So that's sort of where we rapidly realized we'd probably overshot the mark there, and that sort of the airframe was an important piece, but like a small piece of sort of building the whole system. And so things that would become much more important is, okay, if you're going to operate a large-scale delivery business, you need many thousands of airplanes.
Right.
If these take a very long time to build and are very expensive, like you can't build enough of them. You can't source enough of the components. We had to sort of more or less go back to the drawing board of, okay, the architecture is right, but how we're putting them together maybe isn't.
I'm fascinated by that. So when you made the leap to this, did you think you were going to now we're just making the product?
Yeah, I was. This was sort of at a time when I was still building the planes and stuff. So I was like, I'm right. Like this is totally what we're gonna do. I've since sort of obviously come around on that.
That's amazing.
But this is how I built planes in the past. This is sort of how planes were built.
Sure. You were
but
going
it was
with what you knew.
Yeah, but it sort of ended up being fundamentally ill-suited to the task at hand. So we had a sort of.
But that strikes me as a difficult meeting to have.
Yeah, it's one of those ones where it's like maybe not difficult as much as very open-ended. Right.
Right. Hey, turns out we were totally.
It's like, okay, we can't do it the way it's always been done, which is kind of a cool sort of conclusion to get to. But then you have to be like, how are we going to do it?
Right. And then all of these cascading
Yeah.
questions come down.
You have sort of what looked like a very straightforward development process just became very unknown.
Right.
So
Which is both exciting and terrifying.
yeah, no, it's an opportunity.
Fair.
So we looked at sort of, we took a lot of inspiration from sort of how airplanes are built in volume. So like you think like the most airplanes that are built are not like airliners, they're model aircraft.
in terms
of number of planes
sheer
that are
numbers.
built,
Right.
types of materials that are used. And the task at hand was like, how do you get aerospace quality and reliability and performance out of sort of like consumer electronics and hobby type build practices?
Right.
So we did a lot of prototyping, a lot of sort of early efforts on, can you build a foam airframe that has sort of the features resolved to the right size,
Right.
thicknesses in the right spot? Can it be strong enough? Can it be durable enough? We eventually settled on, these are injection molded expanded polypropylene. So it's
that
like
stuff.
solvent resistant, doesn't dent.
It's very
but
durable and impact resistant.
But it's not very stiff.
Ah.
So, so this is actually, these are made at a bike helmet factory.
You went everywhere.
Yeah, so they have is a polycarbonate skin.
They have a high, right, because they have the experience in putting a skin tight to an expanded.
Yeah, because you have all these things, like the part doesn't come out of the mold at its final dimensions.
Right,
it goes through a
right.
heat treat process, it get bigger, it can get smaller.
So rather than figure that whole thing out for yourself, you go to someone who has that.
Go to people who have that
knowledge.
experience. And then you get into like, okay, how do you actually build them? So here's all the different, each one of these is like a different adhesive layer.
Right. Oh, God.
So you got compound curves and all this stuff. So
Yep.
we eventually sort of figured it out. So these are some of the boilerplate ones, but the sort of foam airframes with the plastic parts for reinforcement, plastic covers covering up what were still sort of pretty boilerplate electronics.
Yeah. And every single one of these models that we're looking at was flown and iterated and you
These are
learned
all-
from it working.
Yeah, and that's sort of our general philosophy is like, start with a common architecture and then sort of like make iterative progress towards sort of, a better solution. We refined this design a bit and then got to sort of the first design that we really put into like commercial service, which has a lot of the same build methodologies, but obviously like a cleaned up version of the avionics that's in its own enclosure. You don't have like rubber banded on covers. You have, parts that can be field serviceable. So you can, hook up batteries and things like that.
It's so funny that after with the extreme amount of iteration of so many tiny details, that simplicity is the result.
That's always, it's always like, well, how do we get this part to stop breaking? Like, just design it out of the airplane. These were sort of like, fair weather aircraft. So, they had the performance specs we were looking for, but, they still had exposed motor controllers. These
Right.
were just conformal coated with like an off-the-shelf spray. And they had a stock propulsion system on them. So these are like totally off the shelf. These are like racing quad
Right.
motors and propellers. People talk a lot about like drone noise.
Yeah.
These were legitimately loud. Like they were
Sure,
like,
and I'm actually curious because I noticed like the black propellers over here, how much, there must have been as much iteration on propellers as everything else.
yeah. So that was these ones. Imagine like three racing quads all hovering sort of in unison.
That is a high.
It's very high pitch. It's not loud from a decibel perspective, but the noise is very unpleasant.
Right.
So we operated these in service for a little bit, got a lot of feedback about the noise, got a lot of feedback about what people actually order, sort of all the bits there.
Oh, right, because you have to figure out the payload for what people are going to order.
Yeah, so it's
For a service that doesn't exist yet.
yeah, you're sort of continuously bootstrapping all the answers.
Okay.
But we wanted to go from something that sort of proved out all the elements on sort of like to first order to something that was a more refined product. So this was the sort of next sort of like generative iteration of it, where we waterproof the whole airplane.
Right.
So now instead of like conformal coated boards, you've got little enclosures that everything sit in.
The props are totally different.
Props are totally different.
Is this your design now?
Yeah. So these are now custom, and they were designed specifically to change the noise profile of the aircraft.
Wow.
So to go from that like high pitched whine down to sort of more of a whir, to sort of spread that one peak in frequency out.
Are there interesting compromises in terms of sound and
Yeah. So
flight?
like these are like, this is obvious. Like it's like. If you're just designing around sort of performance and efficiency, like
It's going
noise
to be
is
loud.
secondary.
Gotcha.
So like, these are less efficient propellers.
Sure.
But they are more pleasing. So holistically, they are more efficient, right? It's
Right,
a better
yeah.
product.
And also, the decrease in efficiency can be bought back by the number of propellers that you're actually using?
Yeah, well, it's I think on this one we made some weight trades. We sort of simplified some of the airplane surfaces to like, they don't have the little swoopy tips anymore. But like this became sort of like the mainstay of our fleet for a couple years.
Okay.
Interestingly, sort of all the way back in time, they have the same forward flight propulsion.
Copy.
So these fly like they basically take off like a quad rotor and then they accelerate with these motors.
Right.
Until they get up to speed, they turn these off and they fly around like a plane.
Using much less energy.
Much
for forward motion.
less
Yeah,
energy.
yeah.
And we had always thought like the reason we invested a bunch of time and energy in the hover system was that's like what's closest to people. That's
the
what
last
they're going to
mile.
hear. We thought like, okay, that's what people are going to care the most about. And if you think about it, like if you're ordering something, like you're not going to mind the fact that there's an airplane there because you called it to you.
Of course.
And like if you're in a neighborhood that gets the service, like your neighbors probably use it as well. Like it's sort of part of that neighborhood.
Right.
The multiple neighborhoods it flies over to get to you are not part of that same order experience. So these objectively are not loud in cruise, but they were loud enough that people would notice them.
Fascinating.
So they would you sort of be like, do I hear something? And you look up and you see the plane.
Yeah.
And if you didn't like that the plane was there, you'd be like, oh, well, the plane's there. I know it's there. So the next iteration we went through was how do we make it so that the airplanes were imperceptible to like...
That was the goal, imperceptible.
So it was like... if a plane flew over, you wouldn't even look up.
Right. Wow.
Because if you think about all the people you're going to fly over to get to a delivery, that's like sort of the odds of someone noticing it and sort of being upset about the noise go up substantially. So we applied the same, these were off-the-shelf propellers, perfectly fine for the job they were doing. We went through the same exercise that we'd done for the hover system and did it to the cruise system. And back to the efficiency point, this was a less efficient propulsion system.
Oh, sure, understood.
So if you think about prop design or sort of like moving air in general, like the most efficient propeller would be like infinite diameter turning at like limit as RPM approaches 0, right? You want to take a huge amount of air and move it a little bit versus a little bit of air and move it a lot. And so these are obviously smaller, so to get back to the same relative area, we needed to add another set. And then we had lost cruise efficiency, so we had to gain it back by stretching the wing.
Okay, so I'm curious about this iterative process in this case, where between these two, these don't seem to be changing that much. Is it the case that when you're iterating on reducing noise and getting more efficiency out of that low noise on the wings, there's still work being done on all the other systems here?
Yeah, it's basically, I like to think of it as like you build a bunch of interchangeable construction bricks.
Right.
And each one of those can be sort of standalone in either how you develop it or what problems you're solving. And you happen to assemble them into a rocket ship.
Right.
But if somebody comes along and says, hey, I don't want a rocket ship, I want a tugboat, you take apart your rocket ship, you still have all your standalone parts, and you put them back together into a tugboat or into a cruise ship or whatever. And so that's sort of the general philosophy we've taken on the aircraft design as a whole, is like break the thing up into a bunch of subsystems that you can iterate on their own. And you can have sort of offshoots in the design that don't disrupt the rest of the design.
These airplanes over here look substantively different than the iterations we've just been looking at.
Yeah. As I said, we sort of built all these common building blocks.
Yeah.
But the airplane is just like one version of the construction of those. Now that we've been operating for a while, we've gotten different feedback from the customers, from the partners, sort of what people want. And there was clearly a need to make some airplanes bigger. So, we can deliver the vast majority of packages with the current airplanes, but like there's some stuff like the common thing is like a 6-pack of beer or a container of like baby diapers doesn't fit in the current box.
Fair.
So the task became sort of like, how do we take the common parts we've invested all this time and energy in and wrap a new airplane around them? And Julia here has led most of that effort. And she can walk you sort of through how that evolved.
Now, did you when you go, Julia? So you go to a bigger airplane. Do you end up solving the same problems, or does it present a whole new raft of problems?
You end up solving some of the same problems and then a new raft of problems in certain areas. So if you want to make the payload bigger, you can't just like change the airplane you have. You have to sort of start from scratch or with the building blocks, but you need to size the aircraft for like the payload you're gonna carry and for the mission you're gonna do.
Okay.
But it's a pretty similar configuration to what we used before.
Clearly, is this called the mustache? Because this really should be called the mustache.
We've been calling it the mustache.
Awesome. Is that the first thing you knew, that you had to necessitate a different kind of propeller?
We knew that we needed a much larger propeller, so bigger aircraft weighs more, needs more thrust.
Right.
We were going to need bigger propellers.
What is the reason for using less propellers if you're lifting more?
You might want to increase the disk area. Adam talked about this earlier, like you want to move a lot of air a little bit. There's also a noise component. The slower the propeller spins, the quieter it will be. A larger aircraft is just going to be louder just because you need to generate more thrust. That's kind of the first order scaling. The next scaling is making the tip of the propeller spin slower. So we sort of optimized a little bit for how large of a propeller could we fit on this aircraft without making the aircraft unreasonably large in footprint. We use sort of the same configuration where it's like, I love that I work on really boring airplanes. Like, this is the simplest way to solve this problem. You want to hover into some place, you want to deliver something precisely, you want to go land in a precise location. We have a hover system to do that. And then you want to go fly to your location efficiently. And the best way to do that is a conventional airplane. So we put those two things together. It's the strategy we use for the first aircraft, strategy we use for the second aircraft. It makes a lot of problems simpler. It makes the controls problem simpler.
Right.
It makes the propulsion design problem simpler because you can just design this to be good at hover, and then you can design the cruise propellers to be good for cruise. They're very different operating conditions because of the speed of the airflow that's going into the propeller. That lets you sort of optimize things. The drawback, of course, is that you're now carrying around a propulsion system that is not working for part of the mission, and it's added.
Oh,
weight.
right. It's just payload.
Yeah, it's like added weight. It's added drag to some extent.
Well, and this is the first iteration, and there's two more. Tell me about the progression of your learning on this frame.
Yeah. So this is kind of like that composite aircraft, and this is like the aero demonstrator. Like you make this one super clean. As in terms of just like making it very smooth.
Yeah.
Exactly the configuration you want. You don't compromise in terms of construction or like you build exactly what you want it to be, and then you figure out like where you can sort of deviate from that. So this one is like what we imagined the aircraft to be. And then when we moved on to this one, we had to think about like, okay, how are we going to build it for real? Because even this one is still somewhat composite and like very expensive, like hand built.
Right.
Very expensive to make.
But it's worth going to the expense of building the hyper idealized one to learn about its behavior.
Right, because you have to validate the models. You like
Amazing.
the typical progression is like you start with the model of the thing that you're building, say like, oh, I do the math.
Right.
This is the performance I'm expecting, and then you go test it and find out what the performance actually is.
What the delta.
Right, and then you refine your model, and then you build the next thing.
And this is to figure out exactly how to actually make them at scale.
Right, and so this is where more of the like detailed mechanical engineering comes in. Right.
Oh, that's beautiful. Oh, wow, hot wire cut.
Yes.
Oh, neat.
Yeah, talk hobby stuff, you know.
All right, so where do we go from here?
Okay, so this one This actually was like a little bit later. This was an engineering prototype where some of these parts are manufactured in the way that we would manufacture the real aircraft. And so the mechanical team used this to fit check and put the whole aircraft together and see where they had to make modifications to the parts they had designed.
So this is the current iteration of this design?
Right.
Okay.
This is the final version.
Oh, wow. And you guys are currently running this through its tests?
Right.
Okay. Someday there'll be a point at which you're out in the wild and you hear a sound and you know it's your work.
Yeah, exactly.
That's thrilling. All right, Julia, I can tell that we're standing in front of a wind tunnel.
Yes,
But you guys built this wind tunnel just for your own testing.
we did.
All
That's
right. Tell me about what goes on here.
Yeah, so this is a 2 foot by 2 foot section wind tunnel. It can go up to 50 meters per second. And we mostly use it for propulsion testing. Our aircraft is substantially propulsion system, as you may have noticed. And it's also too big to fit in this wind tunnel.
Right.
So mostly we just use this for testing propellers.
So rather than build a wind tunnel big enough for the whole thing, you're testing the components
Yes.
individually.
Yeah.
Talk to me about the props here.
Sure. So this is the hover propeller that we had on the original 7000 aircraft that you saw in the other lab.
Right.
And then I think you talked about we switched
To
to
this
these
one.
custom propellers. And those were designed to reduce the noise. The main difference has 4 blades, so that one's obvious. But this one is a little bit larger diameter, so that's how we get some of the efficiency back.
Okay.
Move a little bit of air a lot. So like relative to this one, larger diameter, so it's a little more efficient. But having one extra blade means that we can have the propeller spin slower and generate the same amount of thrust. So this one spins at about 20,000 RPM to get us the amount of thrust we need for hover.
Right.
That one spins about 11,000.
Wow, just over half.
Yeah, yeah.
Adam, you were telling me that one of the key innovations you were surprised you had to make was in forward flight propeller design. Can you tell me about this?
Yeah, so here we have one of the airplanes that we first introduced to service.
Okay.
And it's got the custom hover propellers on it.
That are nice and quiet.
Yeah, we focused a lot on reducing the noise in hover.
Yeah.
But it's just an off-the-shelf set of props for cruise. And we thought, well, the plane's up and away. It's, a couple hundred feet up in the sky. And it's legitimately like sort of quiet. Like it's quieter than the conversation we're having.
Yeah.
But it's a noticeable sound. And so we thought that like people would be concerned about noise in hover, but it ended up being they were mostly concerned in noise in overflight.
They were annoyed when they heard the
Yeah, or they would just be like, hey, what's that? And look up and see a plane.
and then they call and complain.
Yep. And so we went through a whole exercise to make the drones more or less imperceptibly quiet in cruise. So
You totally didn't expect that this would.
we didn't expect that this was going to be a problem we had to solve, but we had to sort of listen to the feedback of the community.
Yeah.
We applied the same design we did on the hover motors to the cruise ones.
Yeah, they look very similar.
Yep, same philosophy. They're a little bit higher pitch because they go through faster air.
Oh, okay.
And
they turn a little slower.
yeah, they turn a little bit slower than the stock ones, so that tone is lower. And then they have more disk area, so there's like more prop, so you can move more air more slowly. They're in those trades, you trade a little bit of efficiency for that noise.
Right.
So that's why the wings stretch. So a lot of people look at this and they say, well, you stretched the wing because you were trying to make it go farther. The answer is we stretched the wing because we were trying to make it go the same farness.
This is all about getting back to square one.
Yep.
But silent.
And I think that's one of the sort of classic tropes in aviation is that like sort of everything you changes something else.
Right.
And so this was an exercise where we prioritized the noise element, and we had to make a bunch of compromises on the rest of the airplane.
And we can hear these both.
Yeah,
go,
we're gonna fly both of those. You should be able to hear or you should be able to not hear the difference.
Okay, excellent. Cool. Let's fly them out.
Okay, I can see it. I can't yet hear it. So see that cluster of birds right there?
Yeah, yeah. Okay, yeah. I couldn't hear it long after I could see it. That was so
So that's
cool.
the goal there is like, if you think about what a delivery is like now, like you only experience it when it's actually delivering the box.
Right. When you hear the backup alarm in front of your house. And by the way, this is a tiny fraction of the volume of a backup alarm on a truck.
Yeah, no, you compare this to road noise, like anything else, you're well below all of that. And we can have a normal volume conversation here.
Yeah, we're not having to yell.
And you'll never get it like truly silent.
Yeah.
You'll never get it, but it is like, you want to make it so that it's just part of everyday life, and not in a bad way.
Yeah. Amazing.
There you go.
That is some science fiction, man.